So this lesson is going to finish off the rest of the notes. It's going to be short and sweet, a lot shorter than yesterday's. So colloids is another type of solution that we need to talk about. Sometimes they're also called colloidal dispersions, and it's a suspension of tidy particles in some medium. The dispersed particles are larger than a simple molecule, but small enough to remain distributed. So it has a diameter between 1 and 1,000 nanometers, can contain atoms, ions, or molecules. Because of their small particle size, colloids have a really large surface area. The particles stay suspended because of electrostatic repulsion. Coagulation occurs by heating, so the particles collide so hard that they stick together, or by the addition of an electrolyte. And the particles can be separated by filtration. So things like foams, aerosols, and emulsions are various types of colloidal dispersions. The most common type that you see on a regular basis is fog. The Tyndall effect is what we call the scattering of light by the particles, and it is used to distinguish between a suspension and a true solution. A true solution has particles that are too small to scatter light, whereas a colloid, the particles are large enough to scatter the light. A very good example, we'll go back to that fog example, is if you're driving on a clear night and your headlights are on, you do not see the beam of light passing through the air. You see where the light lands, but you don't see the beam of light passing through the air. However, on a foggy night, you can actually see the beam of light passing through the fog. That's why you don't drive with your high beams on, because it scatters the light back to you in the car. Brownian motion is a characteristic movement of particles that change speed and directions erratically. In the solvent molecules, they collide with the colloidal particles, and so they're going around, willy-nilly all over the place. Beer's law, we've talked about that in the beginning of the year, and we did that take-home lab where you watch the YouTube video using a spectrophotometer. That is something that shows up for solutions. Remember, it is only for colored solutions. It does not work on clear solutions. So that means if it's a colored solution, it's going to be a transition metal, because only the transition metals are going to make the colored solutions that we're going to use, with the exception of zinc. Zinc is a clear solution. It does not make a colored ion. But it's where we do the absorbance is equal to the concentration times the path length times that constant. The symbol A stands for absorbance. That funny looking E, or the little a, is a proportionality factor for the molar absorptivity. B is the path length of the cuvette. Usually a standard cuvette is 1 centimeter. And then the C, of course, is concentration in molarity, which is moles per liter. So the way that it works is you can prepare a standard curve by measuring and graphing the absorbance of light for a certain wavelength by different concentrations. When the unknown concentration is tested, the standard curve can be used to determine the concentration. So for instance, in this graph, if I were to tell you that we had an absorbance of 0.5 or 0.6, you could go over and bring that down, and let's look at the 0.6. So we would take the 0.6, come over here, and then say, okay, come down. So then it would probably be approximately 0.025 moles per decimeter cubed. Okay, so that's the way that works. This is what spectrophotometers look like. The one on the left is usually used with a veneer probe or some sort of other data collection. And then, of course, that old spectrotonic, that is an oldie but goodie. I don't even know if we have those. We had them at my old school. I don't know that I've ever even seen them here at Friendswood. We have the little small ones on the left that work with the veneer probes. So here we have a practice one, and we did an experiment where you compare the solubilities of I2 in water and hexane. A student adds 2 milliliters of water and 2 milliliters of hexane to a test tube. Because water and hexane are immiscible, the 2 layers are observed. The student drops a small purple crystal of iodide into the test tube, which is then corked and inverted. And so the hexane layer becomes light purple, while the water layer remains virtually colorless. Explain why the hexane layer is a light purple. Here's the thing. It says, your explanation should reference the relative strengths of interactions between the I2 and the solvents, water and hexane, and the reasons for the differences. So they're telling you specifically to address both of them, so make sure you do that. So here we have the hexane layer is purple because most of the iodine is dissolved in it. The entrance of the I2 into the water requires a disruption of the hydrogen bonds, which are much stronger than the London dispersion forces in hexane. Meanwhile, the London dispersion forces between iodine and hexane would be stronger than the London dispersion forces between iodine and water. Water and iodine can also interact through a dipole-induced dipole force, but this attraction is insufficient to overcome the differences noted above. And so for that explanation, and that is the College Board explanation, you would get 1 point for recognizing the observation that the iodine is dissolved in the hexane, and that's why it's purple, and then 1 point for the correct explanation of the differences between water and hexane and their intermolecular interactions with iodine. The student then adds a small crystal of Ki to the test tube. The test tube is cork and inverted several times. The iodine ion reacts with I2 to form I3, a linear species. In the box below, draw the complete Lewis diagram for the I3 ion. Now, pause this, and I want you to try to draw upside before you just look at the answer. We actually had that I3 minus ion on the last bonding test, so you should be able to draw that. So it should look like that. You would get 1 point for the correct Lewis diagram. In which layer, water or hexane, would the concentration of I3 minus be higher? And then explain. So you can't just say which layer, you have to explain it to get the point. It would be more soluble in water because of the ion-dipole interactions that would occur between the ions and the polar water molecules. No such interactions are possible in the nonpolar hexane. So you would get 1 point for the correct choice and explanation. And that's it. I told you we'd be short and sweet today. Less than 8 minutes.